All right, we'll continue on here. Let me see. All right, so I'm going to introduce Chapter 7. Which is all about hypothesis testing. Okay. I have not assigned any problems for your homework from Chapter 7. Okay, and well, all the homeworks are optional anyway, in terms of actually doing them. But so, you know, this week as you study, you know, focus on chapters 1 through 6. But I want to at least introduce some of these concepts of hypothesis testing, because the week after the midterm we're going to delve into this a little bit more heavily. So I'm introducing just the topics of hypothesis testing, and then we'll get into it. Oops. Okay. All right. So with hypothesis testing, we're still it's inference, in that we look at a sample, and based on the sample we want to make a conclusion about the population. Okay, so it's still inference, and that's essentially, we look at a sample based on what we see in the sample, we will try to make a conclusion about the population. Okay. And the conclusions we make about the population are based on a pair of hypotheses that we create. Okay, so essentially we create two hypotheses. They are known as the null hypothesis and the alternative hypothesis. And so the null hypothesis is kind of the, quote, status quo. Status quo hypothesis. Essentially, with the null hypothesis is essentially saying that anything you observe in your data can be attributed to random chance. So anything, quote, unusual about your data can just be attributed to random chance. And maybe I should be more specific, can be attributed to the random nature of random sampling. Okay? So if you flip a coin a bunch of times and you get 7 heads, instead of 5 heads and 5 tails, can we attribute that oddity to random chance? That's essentially what the null hypothesis would say. The alternative hypothesis is just the opposite. If we observe something strange in our data, it's because there is something wrong about the null hypothesis. There's something different in the population. Quote unquote odd in our population. Okay, I'll let you guys finish writing that down, and then we'll just try out a silly example here. All right, is this okay? All right, so let's say you have a friend. A friend claims, hey, I'm really good at predicting coin flips. Okay. And you're like, how so? He's like, well, most people, they're only going to be right about half the time because they're just guessing. But me, I can do better than getting them right half the time, all right? So he says, basically, you know, I can correctly guess the outcome of a coin flip over half the time. I'm better than random guessing. Okay, so what do you say? You say, I'm a bit of a skeptic, so let's see if you can actually do this. All right, so we try an experiment. He says, okay, let's do an experiment. So we flip the coin 10 times. And he correctly guesses the outcome 7 times out of 10. Okay, does this convince you that he's pretty good at predicting coin flips, that he's better? Yeah? No? What's your feel? So he says, ha, look at that. You flipped the coin 10 times, I got it right more than half the time. I got it right 7 times out of 10. Boom. Coin flipping superstar. What do you think? You would say, I mean, yeah, but you could have also just gotten lucky, right? Right, so there's part of us that, so we would not accept this as proof. And the reason is that, you know, we feel he could have just been lucky. On the other hand, let's say we flip the coin 100 times, and he correctly guessed it 70 times out of 100. How would you feel then? Do you think he could have gotten 70 out of 100 just from luck? Or do you feel like, oh, maybe there is something to this claim? Okay, and what do you guys think? 70 out of 100, would you be convinced by then that he's better than 50-50 guessing? I would be convinced. Okay, so, or what if we do it? We can blow it to the extreme. 1,000 flips, and he gets 700 of them right. Okay, I would say that's pretty convincing, right? And he's not claiming to be 100% right, but he's saying I can do better than 50%. Okay, so, but here I'll just write this, and I'll say flip, coin 100 times. Correctly guess 70 times. Okay, so at this point maybe we say, oh, there's something to it. Okay, we might believe him. Okay, and in both cases the result is that he only got 70% correct, right? But here we feel like this is not likely to have happened just from dumb luck. Okay, so getting 70 flips out of 100, okay, this, the chance of him getting 70 out of 100 correct by just from luck seems pretty low. And then if we do 1,000 flips and we're correct 700 times, I think this would be pretty convincing. Okay, because is it technically possible that he got 700 correct just from dumb luck guessing? Technically it is possible, but it's so incredibly improbable that we're going to say, yeah, I think maybe there is something to your claim. Okay, pretty convincing. It would be incredibly unlikely for him to be correct this often if he is if there's no validity to his claim. Okay. So I think we have an intuitive sense of kind of what is likely and what's unlikely. And that essentially is how hypothesis tests work. Okay, so I haven't done any math here yet, but we're just saying, we're essentially asking, could the results of my data, could my data have happened just from luck or random chance? And if the answer is it could have happened just from luck or random chance, then we're not convinced that this claim or whatever else is going on is actually going on. On the other hand, if our assumptions about what's going on make it incredibly unlikely for certain outcomes to appear, then that would be convincing to us that maybe something is going on. So getting the coin flip right 7 times out of 10 is not convincing because there's something in us that says this could happen quite often just from random chance. Okay, these ones seem much more unlikely, and so these would be more convincing. Right? And so we can actually do the math behind this. Okay, and so here we have a notion of what's called a p-value. Okay, and the p-value, and this is a key definition that you should memorize at some point, is the probability of observing our data or something more extreme if the null hypothesis were true. So it's the probability of our data. The p-value is the probability of observing our data or something more extreme if the null hypothesis were true. All right, so let's apply this to our coin flip situation here, okay? So our null hypothesis is essentially any results we have could just be a result of random chance. So we're going to just say the probability, so our null hypothesis basically says our friend is just guessing at random. So the symbolically, we would write the probability of a correct guess or correct prediction being correct, or whatever, the probability of guessing correctly is 0.5. Just landing heads or tails, he's going to be right 50% of the time. The alternative, we don't claim to understand how he's doing it, but we're saying our friend guesses correctly over. Over 50% of the time. So our alternative, which we write HA, is P greater than 0.5. Okay, so scenario 1. Okay, 10 flips, 7 correct guesses. What is our p-value? Our p-value is the probability of our data, which is 7 correct guesses. So probability of 7 correct guesses or something more extreme, which would be what? What is more extreme than getting 7 right? Getting 8, 9, or 10 right, okay? 7 correct guesses or more extreme outcomes so that's 8, 9, or 10 correct. Because if 7 were enough to convince us, then 8, 9, and 10 would certainly be enough to convince us also, right? So it's p-value is probability of our data, 7 correct guesses, or something more extreme if the null hypothesis were true. So if the probability of a correct guess is 0.5. Can we calculate this probability? Do we know how to do this? And the answer is yes, we know how to do this. we would have, these are binomial problems, right? So essentially we have binomial with n equal to 10, p equal to 0.5, and j equal to 7, 8, 9, or 10. Okay, so I can solve this doing 10 choose 7, 0.5 to the 7 times 0.5 to the 3, plus 10 choose 8, 0.5 to the 8, 0.5 to the 2. These actually all reduce to 0.5 to the 10, all the way up to 10 choose 10, 0.5 to the 10 times 0.5 to the 0. Are we in agreement here? Am I going too quickly? All right, and if I wanted to do this on the computer, how could I do this? D binom 7, 10, 0.1, 0.5 plus D binom all the way up to D binom 10, 10.5. Or I could also do, there's a few ways, sum D binom 7 through 10, 10 comma 0.5. Okay, so I can do it this way. How, can I use p binom for this also?
Yeah.
What would I do?
P binom.
So I would do 1 minus p binom 6, right? 6, 10, 0.5. Because if I did 1 minus p binom 7, I would miss the probability of getting 7. So I can punch all of these into R. Any of these, really. Okay, so I can do sum D binom 7 through 10. Sorry, I'm using old school R because it fires up faster. And this gives me 17%, or I can do 1 minus p binom 610.15. Oops. Oh, 610.5, okay. And we get the same answer, 17%. So the answer here, our p-value is 0.172. All right. So what this means is that if our friend was guessing at random, he has a 17% chance of getting 7 out of 10 or more just from dumb luck. So because that's pretty high, or it feels pretty high, he would get this lucky about 1/6 of the time, we're not ready to accept his claim that he's good at guessing coin flips. Okay, so our p-value is 0.172. This means even if our friend is guessing at random, he can get 7 or more right by luck with probability equal to 0.172. So we are not convinced, because this probability is high, we are not convinced that his claim is true. Okay? Because the p-value, the probability, is high, we are not convinced that his claim is true. I just want to make sure that this line of thinking and logic makes sense. Yes, question.
What percent would have to be at for it to not be high enough?
Yeah. Okay. So this is a very good question. At what point are we going to be convinced that our friend actually has this ability? Okay. And the answer is, it's up to you. If we're, in this class, we teach from a classical statistics point of view, and so with classical statistics, the guideline is about 5%. If it's lower than 5%, we might be convinced. If it's greater than 5%, we're not yet convinced. That's kind of an arbitrary line that has been established over the course of time, but there's no magic in that value. But yeah, we'll discuss the nuances of 5%, or what's called our significance level, after the midterm. Yeah. Okay. Is this okay? All right. Well, so let's just test out scenario 2, which is exactly the same thing here, except our data is different. So the only thing different about scenario 1 is that, so actually let me copy all of this. And, whoops. Let me get rid of this conclusion here. Okay, so in the second scenario, it's exactly the same thing. Our friend says, I know how to, I can predict coin flips, I'm really good at it. And the only time here is now our data has 100 flips, and he's 70 correct. Okay, so our p-value, how would we get our p-value in this scenario? P-value is the probability of getting what? 70 or more correct just from random guessing, right? So essentially we assume the null hypothesis is true. So the p-value is the probability of getting our data or something more extreme if we assume, or if the null hypothesis is true. So in this case, what's the probability of getting 70 or more correct out of 100 flips if the probability of being right is only 50% each time? Okay, so we can answer this also. We can do a normal approximation to the binomial, or use the computer. Okay, so normal approximation, how do we do this? We would do, we would say x comes from normal distribution with mean 50 and standard deviation equal to, well, it's going to be 5. It's going to be, standard deviation is 100 times 0.5 times 1 minus 0.5, which is also 0.5, which gives us the root of 25, which is 5. Okay. And so our cutoff, what is our cutoff? We go out to 70, and we want 70 or more, so we go cutoff at 69.5. Okay, so my z-score is going to be 69.5 minus 50 over 5, and I get 3.9. So I'm 3.9 standard deviations away. And I want to know what's the area to the right of that. Okay, so I can do 1 minus p norm 3.9, and I get 4.8 times 10 to the negative 5, according to that. Or actually, does your normal table go out to 3.9? No, it only goes to 3.49. So it's off the charts on the normal table. Okay, or we could do so this is with the normal approximation. We can also do it directly with the binomial. I can do sum d binom 70 through 100 given 100 and 0.5, and we can see how these compare. Sum d binom 70 through 100, standard 100 and 0.5. Okay, and so this says 3.9. So the normal approximation is a little bit generous here. So it says 3.9 times 10 to the negative 5. Okay, but both basically we're just saying we have really tiny p-values. So 3.9 is basically 0.00001, 2, 3, 4, 5, 3, 9. So this is about 4 in 10,000. So he could be randomly guessing, but the probability of him getting 70 or more correct from random guessing is only about 4 in 10,000. So it's pretty unlikely, is what we're saying. Is this okay?
Where's the 4.8 by 10 to the negative 5 coming from?
That is coming from, this is 1 minus p norm 3.9.
So we wouldn't be able to find it off of
You would not find it in your table in the book. Okay. All right, and so in this case, because it is very unlikely, technically it's still possible, but because it's so unlikely for him to get 70 or more correct just from random guessing, we are going to accept his claim that he's able to guess correctly over 50% of the time. So I'll say, because it is so unlikely for him to get 70 correct from random guessing, we will accept his claim that he has a coin guessing ability. Coin flip guessing ability. With it's good. May not be the best superhero ability, but I'm sure you can do something with it. Okay. Is that all right? Okay, so this is kind of our introduction to hypothesis testing. And the key ideas that I've covered today are this notion of a p-value and your null and alternative hypothesis. And the idea of us trying to prove something or make a conclusion based on whether the data is likely or unlikely according to our null hypothesis. That's the whole kind of foundation and premise of hypothesis testing, and if you can get that, then you'll be in good shape for the specific tests that we will learn after the midterm exam. So after the midterm exam, we're going to just learn a lot of statistical tests and methods, but this base idea of hypothesis testing kind of permeates through all of these. Any questions? Okay, then I'm going to put a little break.